Really, it's a cycle. Really, this phase of giant molecular cloud starts at the end of the previous phase, which is the death of stars, which I will get to at the end of the talk. So these objects, giant molecular clouds or GMCs, they have between 100 to 100,000 solar masses. They're really, really massive. They cover a large area in the sky, 10 to 100 parsec. For your information, a parsec is at 30 million kilometers. It's really, really sizable. Density is something between 100 to 1,000 centimeter meters cube. You don't care about that. Temperature is really, really low. It's between 10 to 100 Kelvin. For your information, the freezing point of water on Earth is 273. So it's much, much, much colder than that. And anything that is pretty cold, it's kind of frozen in. It doesn't have much movement inside. So these objects are just floating in space, in their place. There's not much going on. And that's how the story begins. So what happens next is, we start with a giant molecular cloud, and something disturbs this cloud, either a supernova explosion or stellar winds or anything. And this turbulence causes some parts of that cloud to be contracted, compressed, and they start fragmenting. And each of those fragments, they start having their own gravitational pull. They pull more of the molecules, the dust, the atoms into them, and they create the seeds or protostars of stars. You know what? And at this point, we call this region a star-forming region. If you look back at this picture, this is a picture of a star-forming region that's called the pillars of creation. If you look at it in the visible waveband, the optical waveband, you just see a cloud floating in the sky. But if you look at it in the infrared, you'd see that there are bright spots in the middle. These bright spots are protostars. These are newborn stars are being formed right now. And as you can see, it's a star-forming region because there's usually hundreds, if not thousands of them in each region. So let's move on. So we know we have giant molecular clouds, they form seeds of stars, and then we move into the life cycle of a star. So there are two main tracks for a star that it follows. There's the average or main sequence star, which is very similar to our sun, and there's massive stars. Main sequence stars are anything below 8 solar masses. So our sun and anything 8 times of that will just follow the main sequence star, which I will explain in a minute. And anything above 8 solar masses, those are massive stars. These go through their lifetimes pretty quickly, maybe hundreds of millions of years, as opposed to billions of years for normal stars. So for an average star, basically our sun, after they form these protostars, eventually they start fusing hydrogen at the center. So you have gravitational pressure closing in, and then you have to have something to support that gravitational pressure into the outward, which would be, in this case, hydrogen fusion, right? It's a nuclear reaction. So you have a lot of dust and molecules and gas pressuring into the core, and the core itself is producing enough energy, enough heat to support against that gravitational pull with the fusion. Eventually, it will exhaust its hydrogen fuel, at which case it will start fusing heavier elements like helium, and then maybe carbon, oxygen, eventually iron. And as it starts moving through these layers, it starts increasing in size, right? So an average sun, like our sun, an average star, sorry, like our sun, would move into the next phase, which is a red giant. At this point, it will be much larger in size, and eventually it will move to a planetary nebula phase, right? And at the last part, it will become a white dwarf. And I'll explain each one of those when I get to them in a minute. The other track that it follows, if it's 8 solar masses and above, it will quickly go into a massive star phase, which is the main sequence, but it would take only a few million years. Quickly goes through a red supergiant, much larger than a red giant, right, in size, and quickly it would cause an explosion, a supernova explosion. Then at the center of that explosion, it leads to a very exotic objects. We recently were able to observe black holes to confirm that they exist, but they were theorized only like 100 years ago. It would only been proven that they exist about 5 years ago. The other type of exotic object is the neutron star, and I'll explain each one in a minute. So for your reference, the sun itself would become a red giant star. In comparison, this is how their sizes would look like. And when it comes to our solar system, basically in a few billion years, our sun will reach the Earth's orbit, so basically it will swallow Earth, but hopefully by that time we'll find somewhere else to live, and that will happen in a few billion years, so no one has to worry about it. This is the very quick phase when it reaches the red giant. At this point, it's fusing helium, and then it will start fusing heavier elements. At that point, it became so large that the outer layers are detached from the core itself. It's not really gravitationally attached to it anymore. So these outer layers would just detach and float into the sky. As I mentioned at the beginning, those giant molecular clouds are at the end of the phase of the death of stars. So these outer layers would just scatter into the universe, take millions, maybe billions of years when they swim, and eventually they will gather around each other and form another molecular cloud, and then the cycle begins again. So this is what happens to the outer layer. What happens to the core? There's still a star at the center, but this star doesn't have any fuel to cause any nuclear reaction, any fusion reaction, right? But it will still emit some light. That's why you see that those outer layers are still being ionized and radiated by the light that comes from the star. That's why you see these beautiful colors. But how does the central star support itself against the gravitational pull, since there's no fusion anymore? So it supports itself against it with something that's called Pauli exclusion or electron degeneracy, which is a quantum mechanical effect. If you've heard about it, if you're interested, Pauli exclusion principle. Basically what it says is that two electrons cannot have the same exact state. And as you compress this object, so these central objects, white dwarfs, they're the size of Earth, but the mass of the sun, right? So they're really massive. But still they don't have a large size as much as the sun or something. So in this case, those electrons are pretty compressed into a small area. And at that point, there's a quantum mechanical effect that was supported against the gravitational pull. And at that point, it just floats in space. It has a very, very minimum light. We cannot really observe the majority of white dwarfs in the universe. And they live longer than the age of the universe itself. So really, the universe itself is just littered with all these white dwarfs. No one can see them, and we can see only a small fraction of them, and they're just floating around. It's pretty sad, I know. So the next thing, which is more interesting, if we talk about the other types or the other track, the more massive stars that can follow, if it's 8 solar masses or above, eventually, because these stars are pretty massive, at the point where it starts, after it exhausts all its fuel in helium, carbon, oxygen, iron, and there's nothing else to fuse anymore. So what happens is it just collapses in. But because of how massive they are, this electron degeneracy principle that I mentioned earlier is not enough to support it anymore. So it keeps even collapsing more and more. So at this point, it causes a massive explosion, and this is what we call a supernova explosion, and it leaves behind a supernova remnant. As you can see, like these objects are supernovae remnant. They look similar to planetary nebulae, so like there's outer layers, there's ejecta from the inner star, but these things, because of an explosion, they travel pretty fast, right? Like pretty fast in space terms, hundreds of kilometers per second or so. So that's pretty fast. And for that reason, these objects are much larger than planetary nebulae. But the effect of this is the same. Basically, you have atoms and molecules and dust just scattered into the universe. It takes millions, maybe billions of years. Eventually, it would gather and would form the giant molecular cloud, and the cycle begins again. But what happens in this case, at the center, the central object is not a white dwarf, as I mentioned, because in the case of white dwarf, you have enough support from electron degeneracy, which is a quantum mechanical effect. Because of these massive stars cannot be sustained without force, it keeps collapsing. So there are two results for that. One is that these electrons will just blend in; they become just a soup, basically. But there's something that is very similar effect, which is called a neutron degeneracy, and that is enough to support it. But in that case, instead of being the size of Earth, it will be the size of a city, even sometimes the size of a basketball. So that's a really small object. For that reason, we really cannot observe the objects that are left, which we call neutron star. Neutron star are really exotic objects, really difficult to observe. Some of them are observed, confirmed, not directly observed, but the effects around them, like, they're predicted to have these massive jets, which we can observe. They're predicted to have like really fast spin. They produce a very quick radio signal that we can listen to. So these are all indications that these objects really do exist, but never directly observed. And I'll leave it at that because this is one of the least understood objects in the sky. The other effect is that if you have the initial star has a mass of 15 solar masses and above, then not electron degeneracy, not neutron degeneracy, nothing can stop it. It just keeps collapsing and collapsing in until it creates a singularity in space-time, and then it creates a black hole. I mean, I'm sure you guys have heard about black holes. They're really exotic objects. They bend light around them. Time becomes infinite, or just time stops when you reach the event horizon. There are all these like really interesting and cool things if you've watched like movies like Interstellar. These things do exist, and it was only confirmed directly through observation only in 2019. Before that, it was only theorized for 100 years, and people believed it, tried to look for evidence, but eventually we were able to observe a black hole. But in the case that was observed, it was a supermassive black hole at the center of a galaxy that was millions and millions of light years away. But still, it was a cool picture, and this is how it kind of looked like. It kind of looks like. So as you can see, the light really goes through it, but because space-time is so curved around it, the light can go around it and come back to us. This is kind of what you can observe in that case. And then with all the scattered molecules and dust and gas, a giant molecular cloud forms somewhere else in the galaxy, and the story begins again. And yeah, that's about all I wanted to say. Thank you so much for listening. I hope it was interesting. And